Can you hear me? Well, yes?
Yes.
It's a real pleasure to introduce the talk of today because, well, Xermán is not only a great scientist, but also a great friend. So we met many years ago in States, and I'm very happy that he's visiting us today. And so Xermán is a research professor of CSIC. He's now at the Institute of Nanoscience of Aragon in Zaragoza. And well, he initiated his career in United States. He did a PhD thesis with a famous author of a very famous book of chemistry, which is Hughie. And also, in fact, the topic of the thesis was more based on organic chemistry. Yes. He was his PhD advisor. Anyway, so then he was occupying different positions in the States as assistant professor and this kind of positions. And he finally moved to Fibertech Incorporated. That was from 1986 to 1989, where he developed laser floating zone techniques, LFZ.
No, continue just.
Okay. Okay, thank you. And this is when we met, and he met so many other people in the Spanish community, and he always wanted, I guess, to come back to Spain or to come to Spain. So finally, he moved here in 1992. Well, a bit before, a bit earlier, at the University of Zaragoza, and finally he started as a tenure scientist at the CSIC in 1992. Xermán is a great expert and pioneer, I will say, in Spain of these LFZ techniques. He was he initiated the laboratory of laser techniques in Zaragoza, in the Institute of Materials of it was the Institute of Material Science of Zaragoza, in fact, before. And he's still developing many active, because he's very, very active research in this field. He has has many papers on growing of fibers of bismuth, strontium, calcium, copper oxide, superconductors, also YBCO. I think you work also on YBCO, no?
Yes, not so much.
Not so much.
I'm working now on it.
But many on one. That was the way we met in Washington D.C. many years ago. He's the fiber, but the LFZ technique. He has worked on euthetic of zirconia and on other for fiber growing also, on niobium superconducting thin films and carbon nanotubes. All this is using laser processing techniques and laser growing LFZ techniques. So this is the topic of his talk today, is based on formation of nanostructures using laser. So
thank you very much. Yes. And usually I have a good breakfast, so I can speak very loud. So I try to wake you up if you fall asleep on this nice siesta time. As Amparo said, we met in 1989, probably, because we went to the MRS in California, in San Diego, where we met the famous Linus Pauling and other famous people. There's some pictures we took. We took many pictures. There you were in my home in the Washington, D.C. area. And I met through Professor Miguel Alario, who just recently passed away. And he introduced me to a lot of Spanish scientists. And then I became friends with many scientists. I also had a connection because I'm from Galicia, and I studied in Santiago, and I had many friends in Santiago. So I had, originally in 1989, I was offered a visiting position in Santiago with Professor Felix Vidal, and that was to teach solid-state physics. But it was only 1 year, and I did my PhD in the USA, and I could not have, and it would take me years to get the PhD title approved here. So they convinced me to go to Daniel Beltran, a common friend, who's a great professor and great solid-state scientist, convinced me to go to Zaragoza, and they insisted a lot, so I ended up in Zaragoza because I had 5 years to get my PhD diploma accepted in Spain. And after 3 years, by chance, I got it accepted. And then I got a position in the CSIC. Meanwhile, I was a professor of physics in the University of Zaragoza in the engineering school. So I taught first year physics. But that was a very good experience. But then I joined CSIC, the CSIC, the Spanish National Research Council, at the Institute of Material Science of Aragon, which is now the institute. We absorbed a nanoscience institute, and now we're called Institute of Nanoscience and Materials of Aragon. So we are too many. We are more than 300 people, I think, in the institute. It's quite large, larger than here. And we do a lot of collaborations. So we have a nice group. I'll show you a picture later. Our group is this Laser for Energy and Materials group. Yeah, actually, Lasers for Energy and Advanced Materials group. And this is, I will explain what this is later. So we are at INMA. This is a mixed institute of the Research Council and the University of Zaragoza. We are in the premises of the University of Zaragoza. And we do a lot of collaborations, in this case, with a group in Liège and BAM in Berlin. And we collaborate with a lot of groups also in Spain, in Seville especially, with a surface science group in Sevilla, of Professor Agustín Rodríguez González Felipe, who is now emeritus. And we continue. We always have projects with them. So you will see some projects which I acknowledge here, which are also usually with the people in Seville. So here there's a lot of contributions from Luis Porta, who is just now got his PhD. Javier Frechilla, who is working on nitrides, on niobium nitride and similar things. From Joaquín Rivera, who is working more on polymers and affected by lasers. And then Elena Martinez, Antonio Badia, and Luis Alberto Angurel are my colleagues in the group, senior colleagues, and we do most of the work together. Alejandro Silhanek is an Argentinian who is a professor in Liège. He's a really bright guy, a really great professor and great expert in superconductivity and magnetism. Jörn Bonse is in Berlin. He's the #1 expert in the world in nanostructures, in what they call laser-induced periodic surface structures, which are made with femtosecond lasers. And Carmen Bao is a colleague in Santiago de Compostela in the Faculty of Optics. And she's an expert in optics, and we work together for many years also. So why am I here? I don't know if this is working, if I'm doing the right thing. This is. Yes. So this is on the left. No, here. Here on the left side. So it doesn't let me.
Maybe it's fine.
Okay. Okay, thank you. Great. This is the origin of the laser lab. This is my first installation. It's the largest cylinder crystal fabrication facility by laser in the world at the time. It was more than 1 meter. It's from down here, it's almost 4 meters high. And it's with a vacuum chamber, so I could work in a controlled atmosphere. And we had a laser coming, a CO2 laser coming through here, some optics here, and special PID control for the growth. So we could make nice crystals, and we could make very nice texture superconductors, which was what we worked at the time, as Amparo said, visco materials. So they are very nice, they melt very nicely, and we could make very interesting materials with that. And this is Professor Rafael Navarro, who has passed away, unfortunately, just a few years ago. So he was a great friend and a great supporter. He's a really bright guy. He's a theoretician, but also in the lab, and was always available in the lab and doing things. And we learned a lot of things from him. It was superb. He got his PhD thesis at Leiden in the Netherlands. So, this is Paco Francisco Lera. He's a great scientist. He's in the School of Telecommunications Engineering. He's a great professor, and he was one of the great experts in superconductivity at the time. And this is another colleague who went somewhere else. This is Ángel Larrea. He's one of the best microscopists in Spain, and he looks really young here. He's unrecognizable only from what you see today. This is Antonio Badia, who I told you before. Luis Alberto Angurel. They look much younger here than they look now, just like me. You know, I'm here. I look very serious and very strange. And this is Yibing Huang. He's one of the big bosses in R&D at Bruker. He's in charge of developing the superconducting cable for all the superconducting magnets at Bruker. He's a really interesting guy. And he was my first PhD student many years ago. So, this was my second PhD student, Andrés Sotelo. He's working very well and very intensely on thermoelectric materials. So he keeps using this system. So at one time, I got tired of this system, and because it was very easy to publish, very easy to do the same, but it was routine. And in science, in my ideology, I did not want to do any more routine. So I left that for the young people to improve everything and do it better, and they do it. So let me tell you what I will do now. I do a lot of things with lasers. And so what I wanted to tell you here is to give you an idea of what lasers can do with materials. So you can imagine I am a material scientist. I'm a chemist, also solid state chemist and material scientist. And so I look at the laser when it comes as if I was the material and I am receiving the radiation. So I can feel what is happening. So this is what I want to transmit to you today, okay? And so for that, I will give you some fundamentals of laser material interaction and what they will call fundamentals for pedestrians. So I hope I can do it in a language that you can understand. I assume I understand nothing, which is probably close to true. And this is how I will talk. Then I will talk about some processing examples so I can relate the fundamentals that I talk about with examples of intense photothermal interactions. That means when we have heat involved, with laser ablation, which can be with heat or without heat, basically, and with other physical-chemical phenomena which are not melting, where melting and ablation are not involved, but they're very interesting. And then I'll give you, rather than conclusions, I will pose some questions remaining that have not been answered yet. So lasers are very varied. You can get lasers commercially in all these wavelengths and some more. There's one that is missing here because it's very recent. It's the blue wavelength gallium nitride lasers. You have gallium nitride lasers which have several kilowatts of power, and they're used mainly to melt and weld metals like copper, aluminum, metals which are highly reflective in the infrared, and there are no UV lasers which are so intense to be able to melt them efficiently for industrial processes. And so the new lasers with their kilowatt powers are very useful. They are semiconductor lasers, gallium nitride, as are some of the others, let's say gallium aluminum arsenide lasers, which emit in the near infrared, around 800, 940 nanometers of wavelengths. Then you have solid state lasers, which usually are emitting in the infrared, in the near infrared, at around 1 micron wavelength. You have gas lasers, which emit in the UV, like excimer lasers. I think Florencio probably is a user of these type of lasers, and there are several wavelengths. You can go down to just below 200 nanometers emission wavelengths and up to near the visible, but still in the UV. And depending on the gas composition of the excimer. And you can also have a CO2 laser. Yes, the greenhouse gas emission laser. So it's a CO2 laser, and this is excited with a discharge, with a 30 kilovolt discharge, but it's not the CO2 which is excited. It's a mixture of CO2, helium, and nitrogen. Nitrogen is around 17%. CO2 is about 7% or so, and the rest is helium, which dilutes everything, exchanges heat. And the nitrogen forms a plasma, and the nitrogen plasma collides. Nitrogen molecules, excited species, collide with the CO2 molecules, excite them. When they de-excite, they emit, as you can expect, very low energy radiation, which is about 10.6 microns. So you have a choice of UV lasers. Now the new UV lasers, more and more, are based on the solid state lasers, which are triple frequency. So with nonlinear crystals, they are doubled and tripled, doubled into the green. So you can take a 1 micron laser, double it to around 500 and something nanometers, or triple it to 355, quadruple it to 266 nanometers, or 257, depending on what you use. And so these are very useful. They're very compact. Many times they are just air-cooled, so they're very easy, and they are cheaper and cheaper. So what was now recently the price of a fiber laser was about 10,000 euros if you buy it in China. Now has gone down to 1,400 euros. So this makes lasers available in the lab and for many processes, which are before were not so easy to get because of the price and so on. So some lasers are very large, like this 2 kilowatt CO2 laser that we have into this laser furnace installation, which is 13 meters long. And so we can treat ceramics and glass in this installation. Or we can have a very tiny laser, which is less than the size of a PC tower. So this is, it only has a control, which is very thin. Just maybe more or less like one of these things that you have here, one of these apparatus. So lasers are more and more miniaturized as we go on. They have many advantages. Usually they're collimated, and they're coherent, and they have properties which allow space and time resolution in their control. So you can dosify the irradiation of a material in space and in time. And this is very interesting. If you see a picture of a non-collimated source, then it can hardly do anything like you could do here. One of the differences that you can do with this, besides going anywhere and having spatial and time resolution, is that with a 1 watt laser, you can get megawatts per square centimeter of power. And with a 1 kilowatt lamp, you can only go up to 300 and so watts per square centimeter. So you can imagine the difference is orders of magnitude. So this changes everything when you interact with materials. And this is one of the advantages of lasers. There are others. You can also pulse lasers and do processes which are based on very short times. And I will show you in a moment. But this is a thermodynamic view. It's a thermal view of what lasers can do. So usually when you irradiate a surface of a material with a laser, if you irradiate at low intensities, you can get heating of an area which you irradiate, and there's no changes of state. We just get some heating, depending on the thermal properties of the material, diffusivity and conductivity, thermal diffusivity and thermal conductivity. Well, heat is dissipated in different ways. But if you increase the intensity, you can cause a change of state, and now you can have solid and liquid. So you can have a melt. If you increase even more, you can generate some vapor above the liquid. And so now you have three states of matter, yeah, solid, liquid, and vapor. But if you go even further in your intensity, then you can also excite this vapor plume, and you have the four states of matter. You can have solid, liquid, vapor, and plasma. And when you have the plasma, species move above the speed of sound. And so when they start moving above the speed of sound, you get shock waves. And you can get very intense shock waves depending on your lasers. Usually this happens with pulse lasers. And if the intensity is high, you can get gigapascals of pressure under that irradiation. So this is very interesting for many applications. And you can see here, this is a picture which represents how complex laser ablation is. So you have heating, melting, you have heat transport, you have thermomechanical stress, very, very intense thermomechanical stress, which causes cracks. You have evaporation of material, you have ejection of grains which are not well bonded to each other, and so you break down the intergranular space in a granular material, and you have a plasma formation with these shock waves, which are very strong and help remove material when it is under an intense thermal shock status. So basically, if you use a continuous laser or very low, very long pulses, you can heat and melt the material. You go towards very short pulse lasers, you can ablate materials. This is an example, but this is an example of melting. You can see this is very fast, right? Do you think this is fast cutting of a stainless steel? It's fast cutting, it's really not bad. Huh? But now if you mix it with ablation, the process is much more intense. And this is 100 holes without any gas assist like before. And because of the shock waves, the material which is cut on the perimeter is ejected because of the shock waves. You don't even need to input gas pressure. So, and you can see it's 100 holes in stainless steel, how fast it is. This is real speed. It's not accelerated. So this makes things very interesting. What this means is that if you do ablation, it's a much more aggressive process than just melting. And it starts to go out of equilibrium. Melting is almost an equilibrium process in this case. And ablation is out of equilibrium, and it's very aggressive, very intense. So when we have intense photothermal interactions, for example, we can do this. We can transform graphite targets which have embedded, for example, nickel and transition metal and a rare earth like nickel and yttrium, for example. You can transform it above 3,000 degrees because this is intensely photothermal with a CO2 laser. It's transforming this graphite target into single wall carbon nanotubes, as you see here. We did this many years ago. I was much younger at that time. And this is what it looks like. When you look at TEM, you can see that the nanotubes stem from somewhere, a point, as if they grew from a nucleation center. And this has been identified with a carbide formation where the metal targets, the metal elements are of the transition element and the rare earth. And so we think that they grow, I think that they grow from this as a nucleation center. And from there, the nanotube starts growing as a single wall nanotube, which is not easy to attain. We characterize this through Raman. I'm not going to the details, but this is a well-known, we have a paper published, extensively published on the Raman characterization, a specific paper with colleagues in Montpellier. We distinguish all these forms. So later on, this was with CO2 laser at 10.6 microns. When we go to 1 micron with solid-state laser, an INMA-CSIC laser, then also pulsed, then we found out that we did not get easily any nanotubes. What we got is other type of nanostructures, and these nanostructures were made up of amorphous matrix and some graphenic type order structure embedded in them. And so we did that for many years, we started to use organometallic compounds and ligands already without metals. We found out just the use of the ligands without the metal was enough to get the same structures. So the metal did not have really a significant effect on the metal structure preparation. And this is the typical structure that you see with this, the product. You have metal particles inside this matrix, and you have to look carefully to see the sort of graphenic structures all around. I don't think I can see them very easily here. Maybe I have some other, we can see them on the, I don't know if I have another one of these, but if anyone is interested, if you look carefully at a high resolution picture of this, you can see that you have graphene planes embedded in this sort of amorphous structure. And the amorphous structure, we found out that it originally came from the fact that we had phosphorus. For example, we use triphenylphosphine as a ligand. The presence of phosphorus generates what is called an intumescence effect. That means the phosphorus gathers all the hydrogen and it forms phosphoric acid, and it prevents the molecule from burning, from undergoing combustion. It just undergoes a pyrolysis, and the pyrolysis yields this type of nanostructures that you see. So the amorphous part of the structure deals with the presence of phosphorus and the chemical reaction in the decomposition of this. But I never published that. I recognize that. It still remains to be published after so many years. But it's a very interesting phenomenon. When we talk about laser ablation is a process which allows you to remove material from a surface, basically. And so I will talk about probably two of these three phenomena. One is what we called initially laser ablation backlighting or laser-induced reverse transfer. It's the same. And I don't know if I'll have, I think maybe I have something about laser. No, this is all the same, sorry. This more common in the literature is laser-induced forward transfer. And this is a printing method, which is very interesting. We also work on that, but I don't know if I have anything here. So here I will talk about laser-induced backward transfer and reverse transfer or ablation backlighting, which is all the same. And this is just something we did in collaboration with, I don't have the publication here, but with a group in Grenoble, which is CNRS, in LMGP, and David Muñoz is the professor of research there. And what we did is combine SALD, spatial atomic layer deposition, with laser processing. The idea in this project was to crystallize selectively the deposits that he made with SALD, which are amorphous. And then we crystallize this. And we did that for copper oxide and zinc oxide because they're semiconductor and they're very interesting for some solar applications. So, but before that, we started doing this technique years before in Santiago with our colleagues in Santiago for optical applications, and just to see if we could generate optical waveguides in glass. And so what we did, this is the simple experiment. We have a glass, a transparent glass, transparent to the laser. We go through the glass and generate an ablation plume in the metal below, which is in contact with it. And so we can generate any drawing, and this will cause the glass to be deposited with metal particles. And that's what you see here. This is the original work. This is the process with a scheme. You evaporate the target, the metal target. It generates a plume. And if it is aluminum, then it generates what is a buried optical waveguide. So it's an optical waveguide which is induced by metal nanoparticles embedded in the glass, so they are protected from the ambient. This is where you can see that how far they go in, and they go into almost 100 nanometers on the inside, but they're not on the surface. And this is because we use a very intense beam. So if we use an intense beam, The kinetic energy of these nanoparticles is very high, and they just penetrate the glass. They're very hot, they penetrate the glass. So, and this is what we can do. We can generate a nicely waveguide and a planar waveguide, and we can guide light through it. We have more serious measurements with a special technique, but this is published. So you can, if you are interested in this, I can send you the publication from years ago. You can also do plasmonic structures with these copper, silver, gold, just evaporating these. And depending on the parameters of illumination with a laser, you can get all sorts of structures. So this is very interesting for other applications. You can also write. And you can see here the process. This is it's very simple dry process. It's just direct the light through the glass into the metal below the glass, and you evaporate the metal into the glass. And you can do that with any type of drawing or text. This is marked permanently, and it's at the atomic level with the glass. So it's inside or outside. In this case, it's outside. This case is inside. Nanoparticles dispersed inside the glass, and this case is the metal on the surface. So you change the intensity of the laser, and you can selectively coat a glass with a conductive metal. And if you do that, this is another experiment that we did with the silver coating. And this is how we explain that it happens. This is in large scale. And you can really design the resistance of these circuits. So you can make a circuit and design its resistance based on how you do the process. So this is very interesting. Here we change the frequency of the laser and we change the speed. In these lasers, when you change the frequency, you change sometimes the pulse width, or you change other factors, and you change the energy per pulse, which is very important. So most lasers, you change the energy per pulse when you change the frequency, and that's how you change these values. But they are very nicely controlled. And so if you make interdigitated circuits like this, you can generate a surface more and more. And it's a very cheap and simple plasma. You can you can do cleaning of surfaces, and you can do cleaning of water, chemical reactions, and so on inside liquid. And so this opens up a lot of possibilities. You can also do other things. You can take, for example, titanium deposited by PVD, that's just a few nanometers of titanium, on a glazed ceramic. And you can shine a sub-nanosecond laser and oxidize this titanium selectively. So make a thicker or thinner oxide and get one of these interference colors, which are permanent. And they are just solid. That means the color doesn't change depending on the angle of view. You don't know why I say that, but you will see why I say that later. So these are solid colors. So you can really engineer colors and get them without any pigment, just by oxidizing this titanium metal and making the oxide. And this oxide is quite stable. So that's when I don't know if I have yes, you will see now the colors, which are different. They change with angle. So this is when you go into other physicochemical phenomena. We have seen melting, we have seen ablation. We will see more melting later. But now let's look into other things that you can do with the lasers. Now you can see this nanostructure, which is very ordered. It's a diffraction grating, very nice diffraction grating. It's obtained. This was the first publication where a large area laser-induced periodic surface structure was obtained. It was 9 square centimeters. The previous one was less than 1 millimeter. And so to obtain these structures, femtosecond pulse lasers are used. And what happens, the explanation with metals of this is that the laser wave is interacting with the surface plasmon polariton wave. And so the resultant interference pattern is what you see here. That's basically it. It depends on the wavelength. So if you use a wavelength of about 1 micron, then you get about 900 nanometers is the periodicity you get. If you use one, like we use in 343 nanometers in the UV, you get the periodicity which is below 300. It's just above 200 nanometers. So you can really get very ordered nanostructures, which are periodic, very nice gratings, and you can do many things with them. For example, you can diffraction gratings, which give you very pure colors, but they are dependent on the angle, as not before, you see? So this is a different phenomenon. There is no pigment here. There is no oxidation. It's just the periodic surface. Very nice colors, depending on how the angle of light and the observer change. So this is the process. The process is very simple. Most lasers nowadays come with these galvo scanners, so very fast and precise. And you just make a drawing with a very light cut program. And this is, it's like a printer, but it's like a scanner printer. And so you can get any type of structure. And you can mix them and get very interesting patterns. You can do this with a green laser. You have much less reflection on copper, for example. And this is all copper. You can do a lot of different combinations and get these very nice patterns, which are also useful for other things. You can also do it for just the sake of decoration. We have published this in Materials Today Advances recently. And in this case, we combined what we did with David Muñoz, which is not the way we did it in the European project, where we deposited a layer of an oxide over a substrate and then recrystallized this layer with the laser. In this case, what we did is we performed the nanostructuring of the substrate and then filled in with the SALD coating, just to see if we were able to maintain that. And we do that, and you can see we can get this very nice, this is the lips nanostructure, and with the coating made by SALD. And you can do these nice things. These are out of, they're not in use anymore. That's why we can use them. Otherwise, I would be in jail at this moment. And but you can see they have the excellent resolution, and also with these knives, with these stainless steel knives. So you can do anything with this, and you can also do other things with something which is more electronically functioning. So something which is electromagnetic in nature, like a superconductor. You can take niobium metal. It's a type 2 superconductor with a TC, with a transition at 9.2 Kelvin and a critical field Hc2 of 9 Tesla. And it has applications in superconducting radio frequency accelerator cavities, cryogenic microelectronics, and it's also very interesting from the fundamental point of view. What you can do. The question is, what could we do if we change the structure of the surface and we generate a nanostructure? Does that affect the superconducting properties? Does that affect its use in applications? And so basically, from one of our colleagues, Antonio Badia, who I showed you before, he makes this simulation, and he can see, depending on the geometry, how you apply these nanostructures, and you can get the magnetic flux profiles penetrating into the film. These are films. So there are films over silicon, for example. They're very thin films. So we need to use the femtosecond laser, not only because we make these nice nanostructures, but also because to treat a very thin film, you need a very short pulse laser so that you don't destroy it, and you can work with it and modify it. And so I'm not going to spend too much time on this, but basically we use a 238 femtosecond pulse laser with an emission of 343. We use 20 kilohertz or 10 kilohertz repetition rates in order to avoid accumulation of heat, because each femtosecond pulse does not input heat, basically, because it's well below the electron-phonon interaction, which takes place in metals, usually around 1 to 5 picoseconds time. So we are well below. So with each pulse, we don't get much thermal transfer at all with the excitation of electrons. But if we use very high repetition rates, then heat accumulates. So then we have a problem with heat. So we try to avoid the problem of heat by working at low frequencies. We make a measurement with MOI, that's a magnetic optical imaging, and we can see how the fluxes, I'll show you in a moment, the flux penetrates the film. This is what we do to avoid damage to the niobium. So we can measure, we first do some single pulse damage and see where we are penetrating completely the niobium layer and get into the silicon substrate. So once we do that, we know how to scan the system, and we can do large areas of the niobium film. And with those large areas, get these very nice LIPS, laser-induced periodic surface structures. So you can see here, this is a lamella observed in TM. And here we can do analysis of this is the substrate. You can see here that we have not penetrated to the substrate. So we are working, we're making these LIPS, but they are in the niobium superconductor, we have not destroyed it. So this is the nice, this is why we look at this. And also we look at what changes in composition takes place with this. So, okay, this is, we use a number of models, the beam classical model of critical state model for superconductors to relate the JC with the field. And this is a King model, which is a modification of this, which is more interesting for films. But I'm not going to spend time on this. Essentially, I show you, this is the difference between the pristine niobium, original niobium, how the field penetrates, and this is after we made the nanostructure. So we change completely how we do this. And this is essentially what we see is that there's an anisotropic JC, which promotes flux penetration along one direction, which is perpendicular to the LIPS that we made, these nano-order structures. And this nanostructure provokes flux channeling along these LIPS, these nanostructures. So the nanostructures are in one direction. So the magnetic behavior of the superconductor, how its properties are affected, is quite different in one direction and in the orthogonal direction. So we are able to control the anisotropy and how this anisotropy conforms what is flux penetration in the material. So we have a new paper, which is already online. It has a 2025 date in Applied Surface Science, and you can see magnificent views there. But I reserve it for Antonio, and if he ever comes to give a talk, or he will give one in Turkey next spring. And also you can see it in color. So it's much nicer than seeing it here. You can see the explanations. Here I show you other things we can do. Texture YBCO. You can see we can now do ablation. This is really ablation. So we are machining this superconductor, which is not easy to machine. I don't know the very technical to machine without damaging it. So this we can machine with a femtosecond laser. This is done with a UV wavelength, and you see I can do any type of geometry. And that was just in circles, and this is just dots. So I'm making here. There are 3,000 pulses per each dot, and it's continuously going over. So we are penetrating on the material, and this affects the levitation forces, how it behaves under levitation, under a magnetic field. And so we find out that if we use, this is a static picture of the different configurations that we can do. And we find out that there's a different behavior towards levitation. And especially we increase the lateral levitation force, which is very interesting for stability. And this is just a broken piece, as you can see, we can work with small, large pieces, broken pieces, without damaging it. And so, although it's broken, I can still do the initial work to do different types of structures on the surface and machining without further damaging this. So this is very useful. So this is, and this is about 40 microns deep. We measure with the confocal. So it's 40 microns deep, which is quite large. Could be even more. It's a question of time. But the material is not damaged. So we're not damaging essentially the material. We're just machining it without any damage. And what you see at the walls of the machining is the microstructure intact. So this is very interesting. Of course, it's done at low, usually at low repetition rates, so we avoid heat. So now let me tell you quickly about how much time I have. At most, okay. Let me just give you this because this is my sponsor. No, but I don't want to make you go asleep. It's a siesta, difficult siesta time. So this is just, I must talk about this because this is my actual European sponsor. So we do this, we do a lot of work with the laser to change surfaces and make them functional. So one of the functional things we do is fighting against ice formation. Ice formation is the #1 problem in aviation. So the most dangerous, so most of the accidents in aviation are because of ice formation, around 400-600 meters above sea level. And when the plane, the plane is in cruising level at 50 or 60 degrees below zero, comes down very cold. It reaches a cloud which is maybe at 600 meters or so, which is full of water, and water condenses, but it condenses as ice. So you get two types of ice, glaze and rime. They form differently, but it's a big problem because it changes the surface of the wings and causes a big problem, or it can avoid movement of the elements of the wing, so it's really a problem. So they try to find solutions for this, and one of the things we did, this is the second project we do, is to change the surface so that ice can be lifted off more easily or not form. Not forming is difficult because of its nature, how it forms, but lift off would be a good help because at the moment they use a lot of energy to melt the ice and remove it. And so the idea is to decrease the amount of energy needed to do that. So for that, we can make circuits, and we can make circuits over a complex structure, for example, where you have ITO, indium tin oxide, over glass. And it's a nanometer thick, could be maybe 50, 100, 200 or more nanometers thick layer. But you have to ensure that this layer absorbs the energy of the laser and that you don't go through to the substrate, or that you go through to the substrate and make a very nice, clean, let's say, interdigitated circuit to make a surface acoustic wave. So the idea is to make a circuit which causes a surface acoustic wave, and this surface acoustic wave vibrating in the megahertz regime causes water or the ice to melt and easily be removed. So we do that, and we are able to machine the ITO, go down to the silica without damaging. We can see it, and usually you can engineer it to make it in different widths and different depths. You need to ensure that you go to the substrate in this case because you don't want an electrical connection. You want a very nice circuit. And so you can get very nice lines in the ITO, and you can see that you can measure at the microscope with EDS. You can see when you have the tin and when you don't have it, so you can really see if you have any remaining ITO layer. And you can engineer depending on how wide you make this, you can engineer the resistance of this. So this is very nice because you can engineer a circuit with a specific resistance, which is ideal for what you want to make. You can also do something else. You can change the water behavior of the surface, change the water wetting angle, and you can do that with combining a microstructure with a nanostructure. And you can see this is stainless steel. It took us 3 years to do this without causing an accelerated corrosion of the stainless steel. So it maintains the properties of the stainless steel. You can see that the wetting angle is very high. It's super hydrophobic, as is this one on this side that you will see here. I don't know if this is, maybe I need to, no. So this is stainless steel. You can also do it in an organic material. For example, you know, the wind generators, the wind electrical generators, they have these very large wings, which can be 50 meters long. And they are fiberglass with a layer of polyurethane paint on top, which is this color you see here. And you can also do that in a femtosecond laser. And the green or UV wavelengths can also generate these type of structures. This is a very high wetting angle. So you can get a very nice, this is a low speed or high speed camera. And you can see this, it really doesn't bind, and a very slow tilt angle will generate this drop to go away very fast. So this is very interesting. So also with Teflon, we can reach a constant, stable 180-degree wetting angle. So that's really super hydrophobic. So you can actually levitate water. You can make a cube and levitate water inside. It never touches the Teflon. So you can freeze the water into a cube, which is perfect. It's not touching anywhere. So this is really interesting from the fundamental point of view. We can see what happens here. This is a single crystal of alumina, random, with a metal layer. This is accumulation of heat. So this is what we don't want. We try to avoid. But in this case, we want to melt. Now it's ceramic. We try to cut it, but we can cut it very nicely by thermomechanical stress we induce with the laser, and also with glass, same thing happens. So this means that materials which are not metals, which are not good heat conductors, have a problem always. And so we tried for many years. We are really good experts in breaking ceramics and glass, probably world experts. I don't know how many samples of ceramics and glass I broke, but I can tell you it was probably well above 1,000. So I became a great expert on that, but that was not very useful. So in the end, I came out with a solution, which was combining volume, heat, with the laser heating. And then, so this is what it is. With scanners, we could make a very nice line, and we could apply it onto inside the furnace into a moving sample of ceramics and glass, and then we could avoid this thermomechanical stress and avoid breaking. So this is the first nice large prototype we made. It was 15 meters long. It was heated by gas, and it had one laser on top, one laser on bottom, and we treated brick on 4 sides, as you see here. So this is there's a line which covers the whole furnace, and all the bricks, although they are misaligned, but still they are very uniformly treated, as you see up here. And so we seal the surface of the brick. We did this because brick has no value. You know, it's very low value. We did not want to give the technology away. Although we had patented, but we wanted to preserve this. And so you can see this with the same composition, depending on how much intensity of the laser and how fast or slow you go, you can get all these different colors and seal them. And then we built a different furnace for another project just to save energy. So this was an electrical furnace, and it was specifically built to treat flat samples. And so we could treat up to 2 centimeter thick samples, which were flat, ceramics and glass. And with this, you can see here, this is not very noisy. This is a refractory brick, which is 10 by 10 centimeters long. So it's very small, but it's not so small. It's 10 by 10 centimeters. It's inside the furnace. It's too small, so some of the rollers are bent, so you will see it going like a ship, up and down. And then it's now at about 1,000 degrees. And now you will see the laser comes in, and it starts melting the top. And this is about almost 1,900 degrees. So we are putting the ceramic at 1,900 degrees, but because it's hot at 1,000, it's much more plastic. It has a more plastic behavior, and it can withstand the thermomechanical stress and not break. So you can make a layer on top, which is completely different, very robust, and very interesting. And you can do that reaction in situ. You can mix calcium carbonate and zirconium oxide and get calcium zirconate, which melts at 2,600 degrees. In situ. In this case, because the substrate is alumina, the alumina flows up because it melts at lower temperature, and you get a composite. But it's a very nice composite. It's completely integrated at the atomic level. You can see here, this is a eutectic of yttrium stabilized zirconia, which also melts well above 2,000 over what we call a porcelainic ceramic. Very nice. These are all published. And you can also get nice decoration over ceramics with very nice colors. You can get red blood color, which is very difficult to get. You get very nice blue and green and all sorts of colors with this. And you can do that. This is an A4 size. When I first saw it, I asked the lady that was working with me to take it off because I thought it was paper. Because I had never seen such nice colors which were not an organic material. So in an inorganic material like this, so this is very interesting. And they are made by inkjet. So they're decorated by inkjet in raw, and then they go through the laser furnace and they come out like this. This is glass. This is glass which can only stand commercially, industrially in the process up to 680 degrees at most. The surface, this is at 580 degrees in volume. The surface is above 1,000. The glass is not damaged. You know, normal glass, this type of glass, which is float glass, can only withstand 60 degrees. And if 60 degrees, you put a heater to your glass window and it will break. We can put this to above 1,000 and nothing happens. And we can integrate any coating into it. So then this is a ceramic, 60 by 60 centimeters, and you can see how good the surface finish is. In fact, we can reach values of about 40 nanometers roughness, which is really nice. And this is a coating of a metal. So we are metallizing a coating which contains an organic metallic salt, and it gives you the metal. Usually, unfortunately, it's a very expensive gold, platinum, or something like that. So, but there are customers who like that. And this is the measurement by Professor Angurel, my colleague, who is measuring this 60 by 60 piece on the confocal microscope. You can see the reflection. And this one in particular gives an average roughness value of about 40 nanometers. So this is, I think Florian will like this more because this is a scanning PLD that we patented at the Max Planck Institute with my colleagues Dieter Fischer and Martin Jansen years ago. And in this case, what we do is we scan the laser, so we can, this is a scalable PLD. You can do it in large areas and continuous. So this is very interesting. But now let me give you some questions to finish. Regarding the carbon nanostructures, you know, we found out that in the mid-IR at 10.6 microns, what we get is single wall carbon nanotubes. But when we go to the near IR laser at 1 micron wavelength, we never get that unless we put some type of, let's say, transition metal with rare earth metal and with a lot of work. It's very difficult to get it. With the CO2 laser, they come out readily and naturally. So The question is if the metals are acting as conventional catalysts or as nucleation centers. I think that they are as nucleation centers because nanotubes stem from the metal sites, and apparently in several studies it has been found that the interface has the carbide of the metal. So it seems that the carbide forms and then the nanotube grows because it nucleates there. But it's not clearly proven. And regarding the niobium films, there are questions that we don't understand. That means we can generate complex nanostructures with very complex geometries, but we don't know exactly whether we have defects at the atomic level that we don't understand yet, we have not seen, that we generate, which sort of follow the geometry of the laser path. We don't know what kind of spatial resolution we can achieve at the interfaces and how the magnetic flux avalanches can be effectively controlled with this criteria. If we were able to control this, we should be able to develop fluxonic devices which depend on how the flux is moved on the superconductor. And there is an interesting theory from a Russian scientist which claims that when you shine the laser into a conductor, what you generate is a current of defects in the opposite direction of the laser irradiation. So this is something that stays there, very interesting. And to finish, this is the group. This is Antonio Badia, Luis Alberto Angurel, very different from the initial picture. And Elena Martinez, these are the senior scientists. This is Luis Porta. His hair is not like that anymore since he got his PhD, short hair. And Alejandro, Javier Frechilla, and Joaquin, they are the remaining graduate students. Alejandro is presenting his thesis. And then this is Andres Sotelo, who is not so young as in the first picture that you saw, and a few other colleagues that we have here. And this is the logo of the group. This is a piece of stainless steel, which has lips all over in a complex manner. This is the real color you see when you change it against the light. So nobody liked the design, but everybody liked the stainless steel. So we all agreed to use it as our logo for the group. But it's really, it's the essence of the lips when you look at it from the decoration point of view. And it's functional. So it's a stainless steel piece, which is just as resistant as the best stainless steel you can buy against corrosion. And so that is the end of it. I'd like to acknowledge this European project and the national projects. And this is our community, which funds us not so much, but we always, it gets a lot of it. For a small amount of money, they get the best acknowledgement always, because we have to put it everywhere for just a miserable amount of money. We get a lot more money from just one of these projects than we can get in 30 years from this, but this is what it is. So thank you for your attention, and if you have any question or anything, just I'm available for you.
Xermán, that was a very, very nice talk, an excellent overview of different possibilities of using laser techniques to prepare or texture or well, process materials. So we can have time for questions. There is any question for Xermán?
Thank you, Xermán, for your interesting and nice talk. I have a question related with the use of the femtosecond lasers. You have shown several example processing or surface modification, either creating lips, either by micromachining of ceramics as ISCO or metals. My question is, when you do this structuration or machining of the surfaces, when is really needed that the laser will be femtosecond in length of pulses, that in principle you could expect that would be energetically less efficient and more time consuming for fabrication of a structure that in some cases you have shown lateral resolution was no less than tens of micrometers.
Yes, right. This is very interesting because you need to avoid ablation. So when we do ablation, we work in a very intense, let's say, high irradiation. That means many watts per square centimeter. And when we do nanostructuring with these lips, we need to avoid ablation and usually melting. If the mechanism with the metal is just the interaction of the laser wave with the plasma polarity on surface wave, then we need to, this has a range of energies you can use or irradiance. If you go above that, then you destroy this interaction, so there's no more interaction to make the plasma polarity and consequent interference pattern. They are also, you can make this by melting. So because melting, you can also generate waves because of the shock waves. But the shock waves are more interesting in the case of nanosecond lasers. So in nanosecond lasers generate different types of shock waves. If you follow the ideology of how you make ablation with a femtosecond laser in a metal, for example, it's not the same bubble which explodes as you have in a nanosecond laser, but it's rather a Coulombic explosion. That means you generate a lot of ionization of electrons. They come out from the first atomic surfaces of the surface, and you have left with a very high level of, or high concentration of positive charges. And it reaches a critical moment where that explodes. But the explosion, I view it as almost a two-dimensional explosion. And you remove material, but you remove material in the sub-nanometric level. So if that is the case, you will not get these nice lips. I know there are lips with, especially with UV nanosecond lasers, you can get lips, and I have seen them, and I have made them. So with nanoseconds, so maybe 20 nanoseconds, even more. So, but with the nanosecond UV pulse laser, you don't get so much heating as you get, for example, with an IR laser. IR laser produces a lot of heating. And when you produce a lot of heating, then everything becomes distorted. You have a nice melt. I think you can, even with the melt, you have, with the, let's say with the pressure waves, you have multiple pulses. You have a nice melt wave going through, which interacts with a laser, not with the laser wave, but with the incoming effect of new waves. And so you have multiple waves. They also give you a certain structure, right? But it's not clear to me if you can do effectively the same thing as you do with femtosecond lasers. I have not seen it. I have seen this. We have seen the structures with nanosecond lasers, but I have not seen that you can make them as orderly and in large areas as we do with the femtosecond laser. So I'm not so sure. If, as you go to, let's say, few picosecond lasers, you can also do that. You can approach that. But you also have to be careful not to overheat. That means you have two effects. One is the irradiance, which causes strong excitation, electronic excitation. If you have a low frequency, a low repetition frequency, you give enough time to the electrons to relax. And if you're below a few picoseconds, you don't excite the phonons, so you don't generate much heat, then it's okay. You can generate that. You can generate these nanostructures. But if you go just above that, they disappear. And first they become like peaks. So you have seen these. Instead of these nice ripples, you get these nice peaks, and then they disappear, and you get something which is more chaotic. But I don't know if I answered your question, but it's a complex question because I agree that with nanosecond lasers, even in the IR regime, you can generate these. These were observed first with nanosecond lasers in 1967 or so.
Yeah, is what
So
I
you know this very well.
not with Xermán that has
No.
that has no spatial coherence like in the
Right. Yeah, the Xermán also the way the beam quality is not so good.
No, I think okay, it was.
But it's another problem. Yes, exactly. So this is I think I have not seen any high order in the long range as with femtosecond lasers, really. So, and they are being used commercially for doing this. So they're making large area scanning in several places in Germany and in other places, just to do very large areas of this. And I know of one application for in metals, for presses, for the wood industry. So if this is the way it goes, that means probably that with femtosecond lasers, you're better off than with nanoseconds. But you're right. I mean, this 1967, it was discovered in nanoseconds. So they had no femtoseconds at that time. But that's very interesting.
Thank you.
Florin is an excellent laser expert, so he knows very well. we can talk and discuss for a long time.
Thermal damages to the substrate during the laser ablation and
It depends. If you go to the nanosecond regime, the damage is usually very high thermally.
starting behavior is also preferable when you are making some disguise.
It's very nice, very predictable with the nanosecond lasers. And we record everything with microphones. You can hear everything. It's amazing. They influence very much. It depends on the material also, because some materials depends on the heat, diffusivity, and conductivity of the material. It depends on how much it absorbs the surface finish, because the surface finish is very important. If you have something which is rough, it absorbs a lot more than something which is very low roughness, like a mirror. And the angle of incidence of the laser beam. So there are many approaches. But if you consider everything else constant, then nanosecond lasers tend to heat very much. The larger the pulse duration, the more heat is involved. You consider that in metals, the electrons which are excited by the photons relax within the pulse in nanoseconds by also passing energy to the phonon modes. Right. So if you input energy to the phonon modes, you make them excited, and this is a great measure of temperature. It's the best measure of temperature you can have. That means when you make them excite, your temperature increases, and you can increase the temperature very fast. So it's very nice and good control to do thermal processes. So we can do a lot of reactions, thermally driven reactions with the lasers, and we do that. We can do melting at high temperatures. We can reach 3000. The graphite target with a CO2 laser, I could measure 3300, not more. But I think the temperature was higher. I did not have a device to measure more than 3300. I can tell you, at least we were at 3300, but this is the limit of my parameter. So I will need to use some spectroscopy to measure more. And so the temperature is very high. The calculation we made with Gamali, who's a very well-known theoretician and experimentalist, and he was in Australia, of Russian origin. He calculated that, let's say, with a nanosecond pulse laser, about 5 nanosecond pulses, let's say you would be at 20,000 Kelvin, sorry, temperature. 20,000 Kelvin. This is easily, you can easily go up to 100,000 Kelvin locally, but this is not the average temperature. Yes, as you go down to lower pulses, to lower pulse duration, you go away from thermodynamics, and when you go to yeah, no, you can see some of the plasmas. For example, you can clean a paint on a surface and not damage the substrate, even if it's very sensitive. My colleague was just cleaning some textile, some very old textile, and in Albarracín, near where I think Florencio knows where Albarracín is very well, close to his origin. And so they were recovering some of these, let's say, 600-year-old documents, and no damage to the substrate, because the pulse is, although the pulse is nanosecond, the energy is consumed by the contaminants. And so you can have a balance. But the contaminants get very hot, but they just go away. So you can play with this. But you can also be very aggressive and melt everything. And so we do a lot of melting and recrystallization. So when you melt something, the way we work with the line scanning, and what is important is not how you melt. It's always how you cool. Because your crystalline order comes with the speed of cooling. And this is related to how fast you move. So if you have a very nice heating front, like the laser allows, the laser line is very nice, very precise, then you move it at a constant speed. This will determine how much structural order you will get, except in a glass. In a glass, we suspect we get medium order, not long range order, like in a crystal. But in a crystal, it's very clear. You can really reach single crystalline state, or you can reach polycrystalline state with high texture. That means high order in the crystallize. In a very, if it's an isotropic crystal like the visco superconductor, then you get very nice alignment of crystals. If it's isotropic, then it depends on how nucleation starts. But we use this for crystal growth to make crystals for lasers for many years. So I grew crystals from almost anything you can think in the periodic table. And many you cannot grow. For example, with lasers, you have materials which get evaporated very readily. But then you can have aluminates, galates, and all sorts of materials that you can grow. They have very stable melts. You can make very nice crystal growth, or you can crystallize in films, which is very nice. Even zinc oxide, you have to be more careful. Copper oxide, you have to be more careful. So heating with the lasers is very interesting because you can have a control in space, which allows you to get a very sudden crystallization front. And this gives you good quality. And also you can control the speed. And then you can control the kinetics of growth. But if you want to do ablation and nanostructure reorganization, then you need to avoid melting. And in ablation, if you avoid melting, you can selectively evaporate components and leave behind what you want. So these are the types of things you can do. These are the 3 types of things. I don't know if I answered your question. I probably got you more confused with so many things, but.
I think we can stop here because
Yes.
we have a long, nice discussion. So let's thank again Xermán for his talk.
Thank you very much.